as you remember from your math courses, in cylindrical coordinates, the position vector of, or the position of the particle is described by three coordinates, two of which are distances, length, and one of them is angle. So if you project the position vector of the particle on the z-axis and also on the xy plane, so the z coordinate here is the exact same z as we had in Cartesian, but now instead of x and y, we use what we call the polar coordinate here, r and theta, where r is the radial distance from origin to the projection point on the xy plane, and theta is the angle measured in a counterclockwise manner from the positive x-axis. So we're going to have r, theta, and z. Okay, and again, if there is no z, it's completely 2D, then we call it polar coordinate. So it's a special case of cylindrical. Now, what about the unit vectors? If you remember, in Cartesian coordinate, I, j, k were fixed unit vectors. Their magnitude was they were always 1, and they never rotate. On the other hand, in tangential coordinates and normal, tangential, normal, binormal, the unit axes, they did rotate. Okay, what about here? So here, the unit axes, the unit vectors, actually not axes, the unit vectors that we use, we call them ER, E theta, and EZ. Now, EZ is always upward in the z direction. So we can say that EZ is exactly the same as what? K. So EZ here is the same as K. It never changes its direction, and it is a fixed vector. But ER and E theta, they do change directions. First of all, how do we determine the direction? Well, if you look from the top here on this picture, ER is in the radial direction R and outward. The positive direction is outward, radially outward. E theta is perpendicular to ER, and the positive direction is in the increase direction of theta. We know theta increases counterclockwise, so E theta, you can see, is, if you look from the top, it's to the left and up. So that's ER, E theta, and EZ is perpendicular to both. So ER cross E theta is EZ. So this is a mix. Two of the three unit vectors, ER and E theta, they do rotate, because as the particle moves on the cylindrical surface, definitely the angle theta changes, and so ER and E theta would rotate, but EZ does not change, does not rotate. It's the same as K we had in Cartesian, and so it is a fixed vector. Now, how do we describe the position of the particle in this coordinate frame? So clearly you can see the unit vector, which connects basically the origin to the current location, is r units in the ER direction plus what? Z units in the EZ direction. So if I add this vector, RER, plus ZEZ, or Z times K, if I add these two, then I'm going to get my total position vector, right? So I can get my position vector. So that's what we say. In the cylindrical coordinate, the position vector R is given by this R, ER, plus Z times EZ. Now pay attention here that these two R's might be confusing. This R and this R are two different things. Okay, these are two different things. This R is not the magnitude of this one. This is only the projection of this R onto the XY plane. So if you want, in order to avoid confusion, I might get rid of this small r and show it with cap R if you want. Now it's less confusing. This is the actual position vector. This is the magnitude of projection on the XY plane. So we can show it like that if you want to make it less confusing. Now, if there is only polar coordinate in other words, there is no z, then the second part goes away and you are all down to RER. Okay, so this is the position of the particle as described in the cylindrical coordinates. Now, how do we get velocity? Well, just we need to get what? A time derivative, right? If you take a time derivative from the position vector, we should be getting velocity. So velocity v is going to be time derivative of the right-hand side. But the right-hand side, you see, each one of these guys is a product. So we have to apply the differentiation of the product rule. So R and ER, two terms multiplied together. Now the question is, do they both have time derivatives, or one of them is constant? And the answer is they both can change, right? R can change when the particle gets radially closer or further away from origin, and ER can change because it does rotate. So both of them are variable. Therefore, it's going to be time derivative of first one, which we show by R dot, right, times the second one, plus first one times the time derivative of the second one. What about ZEZ? It's a product again. Do they both change with time? And the answer is no. This time, EZ, as I said, it's the same as K. It does not change magnitude, it does not change direction, so all we would get is Z dot times EZ. Okay, now, everything is clear except for this guy here. DER over DT, what is this? And in a very similar manner that I showed you in the past in tangential coordinate, if you remember, I showed you that DET over DT was something times EN, and DEN over DT was the negative of that times ET. I can very similar way, I can prove to you that DER over DT is theta dot E theta, and dE theta over dt is negative theta dot ER. Okay, so the proof of them is exactly similar to what we did. So what we want is now theta dot E theta. Okay, so this term here is theta dot E theta. So now if we simplify it, what would we get? We get that velocity is R dot ER plus R theta dot E theta plus Z dot E Z. This is the velocity of the particle in cylindrical. And as I always say in my classes, you do not need to memorize anything. The best practice is always to know the meaning of these terms. Once you know the meaning, you can easily always remember them. So what's the meaning of each one of these individual terms? What is R dot, what is R theta dot, and what is Z dot? Okay, so let's take a look. So if we go back to the cylinder, okay, so my object can go in general on a cylindrical surface, but the radius of the cylinder does not need to be fixed, okay? It can change. In other words, the shape is kind of like a spiral, basically. So the angle changes, the Z changes, and the R changes, okay? So if we can assume a particle on a spiral, let me see if I can draw a shape for you. So let's say this is our three axes, the XYZ, but we also can have a spiral. So if I have a spiral, something like this, and it go, no, wasn't good. Something like that. Again, I'm not the best at it, but just accept it for now from me. So this is the particle here. And this is the XYZ. So when you project it down here and project it here, this distance is your Z. This radial distance is R, and this angle is theta. Right? Now, what's the meaning of each one of these? So as this particle moves along this spiral, what would happen? First of all, the radial distance, this R, that it has from the z-axis can get smaller or bigger, right? The first term is that velocity. So this is assuming that you are not rotating on the spiral and you're not going up and down. All you do is that you go radially, what? Inward or outward in this direction, because the radial distance from the z-axis is increasing or decreasing. That's component of the motion. What about our theta dot? Our theta dot means assume for a moment that your radius does not change and your z does not change. What does that mean? When is it that your z does not change? When is it that your r does not change? Yes, that's when you are on the xy plane and you are going along a circle, right? If you go on a circle with a fixed radius r and the z is 0 or a fixed number, then there is no z dots, there is no r dots, okay? You're just going along the circle. What was the velocity that we derived in the past for velocity for a particle going on a circle? Do you remember? If this particle, this line that connects the particle to the origin, the position vector, if this rotates with angular velocity theta dot, do you remember what was the velocity from one of our previous lectures? This velocity, which was normal to the radial line, how much was it? Let's see if you remember. Yes, you are right. It was what? R theta dot, right? And you can see it, where is that here? Right, this is circular motion. Look at velocity. V is what? R omega, and omega is what? Theta dot. So it was R theta dot. So this term is only due to rotation. This term is what? Assume that you do not rotate, you do not radially go inward or outward, you just go what? Up and down, right? So now I guess you have the meaning of each one of these terms. Okay, so this one is what? Vertical velocity, right? This is the vertical component of velocity for going up and down. This is what? The radial component. Because as you move on the path, you can change your radial distance from the z-axis. And this is due to what? Rotation. Okay, so we can call this rotational component, or some textbook, they call it traverse. So you can have all three components at the same time, and this is basically superposition, putting all three together and get the entire velocity. So now I guess the meaning of it is quite clear, and you never need to really memorize anything. Okay, so this is the velocity of the particle. Now let's look at the acceleration. What happens to the acceleration now? Okay. So, what about the acceleration? I take a time derivative from velocity now, and I get A equals. Now here, I have again a product, r dot er, both are variable, so it is going to be derivative of first one, derivative of r dot is r double dot, times er, plus first one times the derivative of the second one. So this is for the first term. Now plus. Now the second term here has three individual components, r, theta dot, and e theta. And all three of them can change versus time. So we have to use the product of three terms now. So it is going to be derivative of first one times the two others, plus first one times the time derivative of the second one times the third one, plus first one times the second one times the derivative of the first one. The last term, z dot ez, remember ez is constant, so it is only going to be z double dot ez. Okay, so this is what you would get for acceleration, but we need to go and make it a little simpler by using those two rules that I showed you, that der over dt is what? Theta dot e theta, and then d theta over dt is negative theta dot er. Okay, and it is in your lecture. You can see it here. If I plug those, what do I get? So now, if you look, some of these components have ER in them. Let's factor them out. Some of them have E theta in them, and one has EZ in it. So we want to get this important formula for acceleration in this component, and we also had an important formula for velocity and one for position. Now, what terms have ER in them? This one does, and this one does. So what are those? It is r double dot minus r theta dot squared. And what are the terms with E theta in them? This is one. This is one, and this is one. So this one is r theta double dot. These two are the same thing, r dot theta dot e theta, r dot theta dot e theta. So it's going to be 2r dots theta dot e theta. And this is the formula that you have for acceleration. It has 5 components. 2 for ER, 2 for E theta, and 1 for Z or EZ. Now again, do I need to memorize this? No. Okay, so how do I make sense out of this term? So remember, we could make sense out of each component of velocity, so memorizing velocity was not a necessity, right? Because we know the meaning of it. Now, do we know the meaning of these terms? The terms in acceleration, and the answer is yes. So here, let's look. What is this term? This is radial acceleration, right? Assuming that, again, you do not rotate. So for the moment, assume that nothing is rotating and nothing is going up and down. If nothing is rotating, means theta dot and theta double dot are all 0. So this term goes to 0, this one, and this one. And if nothing goes up and down, this term is 0. So the only guy left is this one. So this is the acceleration due to what? due to change in radial velocity. So your r dot term that you had up there is not constant. It does change with time. Okay, therefore you have r double dot. What is this guy here? This is assuming that radius is constant. You're not going up or down. You're just rotating along a fixed circle. Do you remember this term? R omega squared, or r theta dot squared, r omega squared, and the direction of it is negative of er. So instead of it being radially outward, it is radially inward toward the axis of rotation. What was that? You're right, it is the centripetal acceleration, right, that you had here, an. Remember? An was r omega squared, or r theta dot squared, and if you look, the direction of it, instead of outward, it is inward toward the center. So this guy here is our famous centripetal component. This is due to the z double dot is clear, due to change in vertical velocity. Now, what about these two other terms? This one and this one. What are these? R theta double dot, again, this is assuming that you are rotating on a fixed circle with a fixed radius, no up or down, but your omega, your angular velocity, does have time variations. When is it that omega does change? When that you have alpha, right? Angular acceleration. So this term r theta dot, theta double dot, you know theta double dot is alpha. This is r times alpha, and that's what you had here, right? Look at this. The tangential acceleration was what? R times alpha. This is because your omega was not constant. So this is what component? Yes, you are right. This is the tangential acceleration. And I can also call this acceleration. So every one of them so far makes sense, right? Radially inward, outward with acceleration, upward, downward with acceleration, centripetal and tangential. They're all similar to what we had in the past. They all make sense. The only new one is this new term 2r dot theta dot. What is this? When does it happen? How to make sense out of this new term? First, it only happens when radius does change and the rotation happens at the same time. In other words, if you go on a fixed circle, since the radius of the circle does not change, r dot is 0, therefore this term never exists. So you would never ever fill this term if you are going around a fixed circle. Only if you are rotating on something for which the radius does change, you would fill it. For example, if you go around an ellipse, right? If you go around an ellipse, since your radial distance to the center does change as you go around an ellipse, and you're also rotating, both terms exist, so you would fill it, right? So you have to have both. So, first of all, what's the name of this? Where would you see it in real life and fill it? So, the name of it is probably something that you have heard. I don't know if you have heard of it or not. Most probably you did. So, it is called Coriolis acceleration. Most probably you have heard this term, Coriolis. Okay, so that's the name of this term, Coriolis acceleration, which you can see here. Actually, it's one R, not two. So let me correct my spelling. So the Coriolis acceleration is 2r dot theta dot. Now, when would you see it in real life, and when would you see the effect of it? So let's take a look at some videos together. There are two good videos that I have provided links in my lecture for you, and we're going to see them together. Now, since for this lecture, when I started, I turned down, or actually completely shut down the voice of my computer. If I start to show you this video on my personal computer, you're not gonna hear the voice of the person on Khan Academy talking about it, okay? So I have to act as a narrator and talk. Although there is a subscript and you can see below, but I would explain probably once we watch the video together. I would explain a little bit myself again, because the only voice that right now this software is recording is my voice, not the background computer sound. So you're not gonna hear that, and I'll try to compensate for it. So let's look at the first video on Khan Academy. So this is this video, and again, I can hear, you probably can't, and there will be some writing here which explains. So it is talking about the storms and the fact that they spin as they move along their path. And now it says in the northern hemisphere, as you can see, they are spinning counterclockwise, but in the southern hemisphere, they are spinning clockwise. How come? What's the reason? And we're going to see that's due to the Coriolis effect. So let's go forward. So it says, when something is moving on the surface of the Earth, first of all, it will spin with the Earth. So there is some theta dot component. And then, since when you go from the South Pole to the North Pole, or from equator to either poles, the radius does change, right? So it's not really a cylinder, it's a sphere. The radius does change, it gets smaller. So there is the r dot components. Okay, so when something moving on the surface of the Earth, there is both components r dot and theta dot. And now it is trying to explain that, let's go with an example of something that starts in Texas, like an airplane that you want it to fly directly in the north direction. Okay, and then it explains why it would not exactly land north of Texas, like in Oklahoma or Kansas. It would land elsewhere. Okay, so here is trying to explain why they start spinning and why they spin the way they do. Okay, in the northern hemisphere, why do they spin counterclockwise? So let's follow.
If you threw your airplane directly northward, you might think you landed.
Right, so it says if you just threw it north, you expect it to land somewhere in Kansas, Nebraska, or so on. But if you remember, when something is spinning on a circle, the velocity of each point on that is v equal r theta dot. So since different points on the Earth are on different basically circles, right? If you section the Earth with different planes, each one parallel to the equatorial plane, you're going to get different circles with different sizes, and the size of the circles is shrinking, but they all share the same theta dots because they all belong to the same object. So all of the points on these different circles, they have the same theta dot, but the radius is going down, so the velocity is going down. So if you're closer to the equator, the velocity of your rotation is way faster, v is way faster than as you move toward the pole. So now let's keep going.
That means that the paper airplane is spinning faster as well.
So as you could see in this video, it says that the airplane that you are basically aiming directly to the north, it has a bigger angular momentum compared to if you have to start the flight at somewhere like Delaware or so. Because the points at Texas, they are rotating on a bigger radius, and all of these points, they all share the same theta dot of the Earth, the spinning velocity of the Earth, but the radius here is smaller than in Texas because Texas is closer to the equator. So the term v equal r theta dot is bigger for Texas than for Delaware. And so this excessive angular momentum that this airplane has in Texas with respect to Delaware is not just going to go away. Actually, its angular momentum is conserved because there is nothing to make that angular momentum go away or increase. We're going to look at this topic in chapter 16. It's called conservation of angular momentum. And because of that, this is basically forcing this point when it goes north, since it cannot get away from that excessive angular momentum, it is like now it has to rotate a little faster than other points on this line, on this latitude line, on this same latitude as Delaware. So it makes this point to go faster than them because it still has some angular momentum that these points don't, and so it basically moves ahead of them. And instead of coming right here to the north of it, now it moves forward to the right. So when you look at it point by point, instead of this guy directly going upward, it looks like this point is curved this way to the right. Okay? So, and then the opposite of that happens in the southern hemisphere, because as you get away toward south from the equator, again, you're gonna lose the radius, you're gonna lose velocity, you're gonna lose momentum. So if an airplane is heading south, then again it has to shift to the right to have that momentum conserved.
The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left.
So now it looks like this airplane is deflected basically downward and to the right instead of upward to the right. And so you see, if you look at the direction of rotation that these two will cause in the northern and southern hemisphere, they are actually opposites.
Have to do with hurricane spinning? Well, in the center of
Okay, so did you get that? It says the center of the storm is a low pressure area and the surrounding is high pressure. So you expect the streams to always move toward the center. Okay, so you have what? You have radial motion, r dot. And now, what happens? Because of the Coriolis force, because as these streams move toward the center, they are changing latitude, right? They are getting closer to the center, so they are changing their latitude, and because of that force, now you get what?
In the northern
The deflections.
hemisphere, the volumes of air on both sides.
Remember that airplane that was flying from Texas to north, it was deflected to the right, so that's this bottom arrow. Now if you go to the south, you're going to be deflected to the left, and the same happens for the other arrows. So if you look at all these arrows, now what do you have? Now you have a rotation.
Its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens.
In the southern hemisphere, do you remember the plane that was going south from somewhere like Brazil or so, right? It was deflected to the right and downward. So the opposite happens to this one, and the rest of them a similar thing. So now you have what? A clockwise rotation.
Storms spin around the eye in a clockwise.
Okay, so you clearly can see this important Coriolis effect. Why the storms have rotations and why the rotations are in different directions in northern or southern hemispheres. Okay, so it's a very important thing. Another one that is quite interesting in real life is when you have snipers and you have long range shooting, okay? Then again, this Coriolis effect would come into play. So let me show you that, because that is also quite interesting. Again, I have to talk over the video because you probably cannot hear the sound of it. So here is the guy that is using basically a sniping rifle, and he's going to shoot long range, one time aiming to west, one time aiming at east. Okay, and look what happens. So he's saying that if you're looking west and shoot, you're gonna, even if you aim it exactly at the bullseye, when you shoot in a long range, you're gonna see that you actually hit below the bullseye, but if you aim east and do the same, you're gonna hit a little above the bullseye, okay? So although it's probably the same distance, it's just changing the direction of shooting would make it hit above or below the target, and that is because of the direction of r comparison of r dot and theta dot, right? Because the theta dot for both of them is the same, but not r dot is different for each one in different direction. That's why this force will be different. Actually, we'll see later in one of our future courses, chapters, you see, when we want to write all of these terms in a vector format instead of scalars, the Coriolis term, this term here, can also be written as 2 omega cross v. Okay, when we study rigid bodies later, I'll show you in chapter 17, if I'm not mistaken, the chapter for kinematics of rigid bodies, we write it like this, where v stands here for r dot and omega stands for theta dot in a vector format, and or vr if you want to call it. And since this is a cross product, if the sign of one of the term changes, the whole thing would change its sign. Okay, so if this is the same, but this one changes in the opposite direction, the whole thing would change its direction, and that makes the force, the Coriolis force, to either be upward or downward, and making the bullet to hit above or below the target. And here he is demonstrating it. So here we go. First he shot west, now he changed and shot east. He's turning the table and shot east. And now take a look. This is when he shot west. As you clearly see, the location of the bullet hitting is clearly below the target, the 3 black dots compared to the white dot. So this is when he was aiming west. And now this is when he shot east. Look, you see they're mostly what? Above the target. Okay? So it does matter to the snipers that they consider Coriolis effect, because it's a long-range shooting. And although the Coriolis force might be small, but in the long range, it will make a significant deviation from the target. Okay, so they have to keep that in mind. Okay, so hopefully now you feel a little better about this new term. So a couple of other things that we have to look at before we start doing an example together is, if somebody says, what is the magnitude of velocity of the particle at any point? Well, we know velocity has 3 components, so the magnitude of velocity comes from the square root formula. So it's going to be square root r dot squared plus r theta dot squared plus z dot squared. And similarly, if somebody says, what is the magnitude of acceleration of the particle at the moment? So you have to take the whole radial component, this coefficient behind ER, square it. The whole coefficient behind E theta, you have to square it, and then Z double dot square it. So this is the magnitude of acceleration in general. Now, if it's polar coordinate, which means Z is 0, then this term would go away, and this term would go away. Okay? So it is quite clear. Now, I would like with you to look at problems 13, 145, and 146 together at the same time, because they are very good problems. They involve some chain rule that I want to do a little practice with you, and we're going to go over them. By the way, any topic that I cover, any chapter, any topic that I cover, there are 2 types of problems that we're going to solve. Either the problem is an example inside the text, like, let's find one. Okay. Mostly problems. It says examples, I think. Here. Like example 3.4. Well, these examples are solved and explained in your textbook. So if you want to look at their solution on the top of my lecture, you can go and look at your textbook, okay, because these are inside the chapter. But these ones that are, say, problem, these are the end of chapter, and you don't have the solution inside your textbook. But any problem, any end of chapter problem that I solve, I also have provided the solution to them separately on Canvas for your own reference. So if you go to Canvas, if you go under modules, under lectures, okay, so you see here, chapter 13, then what? Chapter 13, solution of the problem. Chapter 14, problems. Chapter 15, problems, okay? So if you click on this one, this should provide you with the solution to the end of chapter problems that I have in my lecture. Okay, so if you miss anything, you can always refer to them and look at those solutions, although I think it's better that you first pay attention to the lecture, because I go into more details than the solutions, and then come and look at them. So here is this file, and the problem we are going to solve are 145 and 146. So we're gonna find them here. Okay, and you can see the numbers. So let's get started on this problem. So in this problem, there is a color that is moving on a semicircle as a guide, and one end of it is at the origin, the other end is at some diagonal distance of 2r. And we describe the position of this color on this arc. Instead of using x and y, we're describing using r and theta, where r here is the radial distance of the color from the origin, and theta is the counterclockwise angle. Now, at this moment, the angle is 25 degrees. The rate of change of rotation, theta dot, is 4 radians per second. And theta double dot, the angular acceleration, is 0. You want to find the magnitude of velocity, which is this guy. In this case, there is no z, so it's this one. The magnitude of the velocity, and then what? The magnitude of acceleration, which is this one. Again, there is no z here. It's just two-dimensional. So you have to apply this formula for magnitude of acceleration and this formula for magnitude of velocity. You have to find those terms, okay, and then apply it, which involves using chain rules. So first thing first is, it says r is 2 cosine theta. It says the relation between this radial distance from the origin to the position of the color and this angle theta is r equals 2 cosine theta. Where do you think it is coming from? So let me clarify that first. Okay, so you have this arc. This is your particle. This is the radial distance, and this is the angle. So clearly you see as theta changes, this radial distance does change, right? When theta is 0, you have the max distance, and as theta gets bigger and bigger all the way toward what? Pi over 2, 90 degrees, you go to 0. So it's a decreasing function of theta from theta 0 to pi over 2. But what kind of function? The problem says 2 cosine theta, but where do you think they got that? First of all, this diameter from here to here is 2 units. Okay? So now let me ask you, if I connect this point to the other side of the semicircle like this, what angle is this guy? Yes, since this angle is inside the arc, right, both of the edges are chords of the circle, and it is in front of a semicircle, the size of this angle is half of the angle in front of it, and the angle in front of it is 180, half of the circle, so it's half of that, which is what? 90 degrees. So this triangle is actually what? A right triangle. And so r here is adjacent to theta, and hypotenuse is 2, so clearly r is what? 2 times cosine theta. Okay, so that's the first thing that we can show why that's the way it is. Now, what does the problem give us, and what does it ask us to find? It says at the moment theta is 25 degrees, theta dot is 4 radians per second, and theta double dot is 0 radian per second squared, right? And then it says, what is the magnitude of velocity? What is the magnitude of acceleration? We know magnitude of velocity, if there is no z, which in this case there is none, was square root of r dot squared plus r theta dot squared. And then the magnitude of acceleration is square root of r double dot minus r theta dot squared, the whole thing squared, plus r theta double dot plus 2r dot theta dot, the whole thing squared. So this is what the problem is asking. And the question is, from all of these terms under these square roots, which one of them do we know, which one of them we have to find out? Clearly, if there is a theta, which there is none, we know it. If there is a theta dot, we know it. So this one I got, this one I got, this one I got, and then theta dot double dot is 0. Good. What about the r dot, and r double dots? Well, we have to find them. The r is not hard. All I need is to plug in that 25 degrees into 2 cosine theta, and it gives me what? The r, which is what I need here at that moment and then here. So there's going to be 2 times cosine of 25 degrees, right? And the problem has that value here. So if you want r, it has given me r, it is 1.81. Okay, so this is 1.81. I got that. So r was a plug and play, that was nice. What about r dot and r double dot? How do I find them? To do that, I need to get time derivative of r. And the question is, where is it that I can take a time derivative from and find r dot? Well, that's the only equation that you are given, this guy here. Okay, you have to take time derivative from both sides of this equation to get what? R dot, of course. So I'm going to bring this, and I'm going to get time derivative of that. Let's see if I can zoom. Okay. So time derivative of r is r dot. Good. What is the time derivative of 2 cosine theta? Yeah, I know most of you would immediately say it is negative 2 sine theta. But that is not completely correct. It's partially correct. Anybody knows why? Yes. Because what you did here, you took derivative of cosine theta with respect to theta, and you say it's negative sign. You did not take derivative of the right-hand side with respect to what? T. So what you need here is the chain rule. Why? Because you're taking the derivative of cosine of theta, but with respect to time. Well, yes, if I had derivative of cosine of theta with respect to theta, the function with respect to its own variable, that was negative sine theta. But here I'm taking derivative of a function with respect to another variable. And the only way to carry this and find it is using the chain rule. So in chain rule we say, well, I cannot take directly derivative of theta with respect to t, but what I can do is I can take derivative of cosine theta with respect to theta, but now look, the denominators are different. To make them equal, I multiplied by a d theta and divided by dt. It is kind of like what? You're canceling these 2 thetas. They are the same thing, right? Now, what is this one? Yes, I know from the past that this is negative sine theta. Good. What is this one? Derivative of theta with respect to time, what do we call it? Yes, we call it theta dot. So this one is going to be what? Negative 2 sine theta times theta dot. That is very important. So if you say, where does that theta dot come from? It comes from the chain rule. Okay, so now you can plug the numbers. You can say, what is r dot that I need here and here? It is negative 2 sine of 25 degrees times theta dot, which is 4. Right, so it's negative 8 times sine of 25, which if you calculate, the value is negative 3.38. Okay, so this r dot here is negative 3.38, and this one. Right? And again, r was 1.81 here. So the last term that I don't know is r double dot. If I know that, life is good. How do I do that? Again, I use this parametric equation that I have and take what? Another time derivative from that. Now, one of the big mistakes that some of my students made in the past, and some of you hopefully, all of you should avoid it, is do not take time derivative from this guy. You might say, well, r dot, let's see, is negative 3.38. So if I take time derivative, then r double dot is what? 0, because it's a constant. That is wrong. You are taking time derivative of the final answer, not the equation. So never take time derivative from because this number, this thing here is only valid for one time point where theta is 25 and theta dot is 4. When we take time derivative from something, or any derivative from anything, they should not be momentarily equations. They should be equations that are valid for all different values of the variables. Okay, you take the derivative from y f of x, not derivative of f of 2, because f of 2 is just for one point. You know, derivative needs a point before and a point after. Derivative with respect to time needs a time before and a time after. It is only for one time point. You cannot take time derivative. It's just, so never take time derivative of the fixed number. Take time derivative of the general parametric equation. So now, if I take derivative of r dot, it is going to be r double dot. Good. This negative 2 is a constant. I keep it. And I have now sine theta, theta dot. I have to take time derivative from sine theta, theta dot. And if you know, since both of these terms are time variable, I have to use the product rule. So it is going to be the derivative of sine theta with respect to time. Remember, everything is with respect to time. Times theta dot plus sine theta times time derivative of theta dot. Okay? So I am using the chain rule. Again, I have to use the chain rule. Here, first, I use the product rule. Now, in order to calculate this term especially, because this one is easy, right? What is derivative of theta dot with respect to time? Yes, it's theta double dot. No big deal. But for this one, again, I have to use what? Chain rule. So I come back here, and I say this time I need to take derivative of sine of theta. With respect to t. And again, since these are two different variables, first, I take the derivative of sine of theta with respect to theta, and then derivative of theta with respect to time. Now this from calculus is cosine theta, but you also have a what? A theta dot. So if I come back here, this guy is going to be cosine theta times theta dot. And so if I simplify it, I get our double dot is equal to -2 times what? Look, it's cosine theta, there is a theta dot, and there is another theta dot. So I'm going to get cosine theta times theta dot squared, and then -2 times sine theta times theta double dot. This is the correct way to get our double dot. And now I plug in the numbers, 25 degrees, 4, and 0. And so if I calculate the number at that point, that moment for our double dots, the number is going to be -29 meters per second squared. So now I can go back here, and wherever I have our double dot, I say it's what? -29. And now all I need to do is to use my calculator and calculate the magnitude of V, which will be 338,725. Okay, so 338,7.25, and I'm using the command norm in MATLAB, which gives you the magnitude of a vector. So this is going to be 7.99. I can round it to 8. So this is almost 8. And then if I plug in for acceleration, I would get this vector, which is 58 and 27. Okay. Which is 63.98.